Welcome to calculating the pH of strong acid solutions. So we've already learned about how to calculate pH in the last video if we already know the hydrogen ion concentration, or if we know the hydroxide ion concentration. So here, a strong acid, remember, completely dissociates in water, and this means that the hydrogen ion concentration will be the concentration of our acid before it dissociates, as long as our acid is at least our acid concentration is at least 1.0 times 10 to the minus 6 molar. If our acid concentration is at least 10 to the minus 6 molar, then the hydrogen ions that are formed from the autoionization of water will be negligible compared to our protons formed from the dissociation of our acid, and then we can ignore the autoionization of water. If our acid is really dilute, so it's less concentrated than 1 times 10 to the minus 6 molar, then things get more complex, and that's really beyond the scope of this course to get into. Just like this, if we want to calculate the hydroxide ion concentration of a strong base with a concentration of at least 10 to the minus 6 molar, it's simply the concentration of our base. Again, this only works if we have a strong acid or strong base. Doesn't work if we have weak acids or weak bases. That assumption breaks down. So this means that in order to calculate the pH of our strong acid, let's look at some example. So suppose we have a concentration of 0.1 molar hydrochloric acid, and we want to know what the pH is. So we know that hydrochloric acid is one of our strong acids. You need to have those 6 strong acids memorized. So all of our hydrochloric acid will have dissociated into the proton and the chloride ion, and this means that our hydrogen ion concentration is 0.1 molar, and this means that now pH is equal to minus log base 10 of the hydrogen ion concentration. Well, we know that hydrogen ion concentration is 0.1 molar, so we can plug 0.1 in there. So pH is minus log base 10 of 0.1. Log of 0.1 is negative 1. Negative times negative gives us positive, so the pH there is 1. So let's look at the pH of a strong base. So suppose we have a 0.1 molar sodium hydroxide solution, and we want to know what the pH is. We know that sodium hydroxide is one of our strong bases. Remember, the alkali metal hydroxides and alkaline earth metal hydroxides, those are all strong bases. So all of our sodium hydroxide is dissociated into sodium ions and hydroxide ions, which means we know the hydroxide ion concentration is 0.1 molar. So we know that our hydrogen ion concentration and hydroxide ion concentration are related by the autoionization of water. So we can rearrange this Kw equals hydrogen ion concentration times hydroxide ion concentration. We can rearrange that to get hydrogen ion concentrations on the left, because we know the value of Kw is 1.0 times 10 to the minus 14. And now we know that hydroxide ion concentration is 0.1 molar. And that means when we solve that, we get the hydrogen ion concentration is 1.0 times 10 to the minus 13 molar. And that means when we plug it in, pH is equal to minus log base 10 of the hydrogen ion concentration, which is minus log base 10 of 1.0 times 10 to the minus 13. The log of 10 to the minus 13 is negative 13. You need to keep that negative sign from in front of the log, so negative times negative gives us a positive pH of 13. So that's one way we could calculate it. Or, once we know the hydroxide ion concentration, which we knew 2 slides ago was 0.1 molar, we can then find the pOH, and then from there convert to pH. If we know pOH is equal to minus log base 10 of the hydroxide ion concentration, and we know the hydroxide ion concentration is 0.1, log of 0.1 is negative 1. We need to bring that negative sign over from in front of the log, so it's positive 1.0. We know that pH is equal to 14.0 minus pOH, which now we know is 1.0. So pH is equal to 14 minus 1, which is 13. So that was calculating the pH of strong acid and strong base solutions.